unheard of.
So for people who don't know me, I'm Robin Schofield. I'm over in the School of Earth Sciences. That's across the other side of campus. And it's my pleasure today to introduce Sonya Fiddes. Probably no introductions. You are all here to support her in her creation seminar today. I'm of Sonya's supervisor, so we have Matt Woodhouse here, Todd Lane at back, as well as lots of support across both Earth Science here in the college. So Sonya has been at the University of Melbourne. She went right through her undergraduate studying meteorology, and then she took a year out and went down to the Bureau of Meteorology, and then came back to work in Earth Sciences, and from that time been based here in the college. And also, while she's moved around Melbourne Central, her PhD has taken her up to Queensland, across to Western Australia, down to Antarctica. And so I'm hoping we see some photos. No photos. That's not. All right. And obviously, the question posed in Sonya's PhD is really about what's the climate implications if we lose the reef, and what is the general understanding of dimethyl sulfide, a compound which comes out of corals. What does that do to our climate, and what in aerosols and clouds? I'm going to hear all about that from you, so I'm going to sit down.
Keep that one. Yep. Thank you, Robin, for that nice introduction. I'd also like to just acknowledge the traditional custodians of the land, the Wurundjeri people, and pay my respects to their elders past and present and emerging. So first of all, I'd also like to thank a lot of people. So my supervisors, Robin, Matt and Todd, for the wonderful support they've given me. Of course, the Climate College, it's been such an awesome group of people to be a part of. The ARC Centre of Excellence for Climate Systems and Climate Extremes have supported me through the whole PhD and given me heaps of great opportunities. And also to my partner, friends, family and cat for looking after me. And I have a whole slide of cat photos. A PhD can be quite a long process, but I think I've had such a great support network. It's been quite a good experience. So thank you. So in this seminar, I will go through the context first and just explain a few key things that you need to understand to follow my, I guess, result. Then I'll go through what this PhD wants to achieve. I'll talk to you about the tools and methods I've used to do this, and then we'll go through the results. And then we'll talk about what these results mean and what this means for the broader climate community, literature, things like that. So first of all, context. What is DMS? What is an aerosol, and what do they have to do with corals? So dimethyl sulfide, as Robert said, is a chemical compound, and it's produced by marine organisms. So not just corals, but algae, phytoplankton, sea grasses, seaweed. So if you've ever walked along a beach and thought, oh, it's a bit stinky, you're smelling DMS. Okay, that's what you're smelling, dimethyl sulfide. An aerosol is any solid or liquid particle suspended in a gas. Okay, so we've had a lot of experience recently of smoke haze. Okay, the aerosol particles. Things like dust, sea salt, black carbon. And in this PhD, we're particularly interested in sulfate aerosols. Okay. And aerosols are important because they interact with radiation and cloud. I'm going to explain to you how they do this in a moment. So what do these have to do with corals? As I mentioned, corals DMS, and so there's a theory around, I guess, or some observational studies suggesting that they might have because they produce DMS, which turn into an aerosol, they might have an impact cloud. So we'll go through this very carefully. We have corals in the ocean, okay, and warm water, and it might be warming up. So corals not only produce DMS time, but if they're stressed, they tend to produce more. So if the water is warm, if they've been exposed by tide or nutrient in the water, if they're stressed, they'll produce more mess. So corals are producing MS. This is released into the atmosphere, okay, where it undergoes a whole series of chemical reactions. I'm not going to go into to produce sulfur dioxide and eventually sulfuric acid. Okay, sulfuric acid is what we call a precursor aerosol gas. Okay, so it's a gas that can either grow aerosols. So if there's a pre-existing aerosol particle, it will condense onto that existing aerosol growing, or if conditions are just right, it will nucleate into a new aerosol, a very tiny particle. Okay? So we have aerosols in the air already, and by producing DMS and then that turns sulfuric acid, it can grow aerosol or more aerosol. Okay, hopefully everyone's with me so far. Aerosol can interact with climate in two main ways that we'll talk about. First, we have direct effect. So if we put more aerosol into the atmosphere, the particles physically block sunlight, okay? and they can scare it and reflect it. So by putting more aerosol in the atmosphere, we can block sunlight from reaching the surface. Okay, so if you remember, a week or so two back when serious smoke in Melbourne, a lot of sunlight was being blocked. Okay, so it's the same process, and that can have a cooling effect at the surface. The second way, the second aerosol effect, what we call an indirect aerosol effect, and it's where aerosols interact with clouds. Okay, and there's a few different things going on here. First of all, by putting more aerosol into the atmosphere, you are basically creating more particles for which water can condense to. So for a cloud to form, you've got to have both more availability, so the water, but you also need a surface for that water to condense to form a cloud drop. Okay, by putting more aerosol into the atmosphere, you're creating more cloud droplets, which can result in clouds being brighter and last greater longevity. The other effect of this is by putting more aerosol into the atmosphere and therefore creating more cloud droplets. For a cloud droplet to turn into rain, it basically has to grow heavy enough that it falls out of the sky. So the more droplets you have in the atmosphere, if you imagine the same amount of water is available, it means there's a great surface area. So those droplets are going to grow as fast, which means it's going to take more moisture or longer for them to rain out. So they effectively suppress precipitation. Okay, so less rainfall is expected when you put more aerosol in the atmosphere. Anyway, by having sort of brighter and longer clouds, you're also reflecting more sunlight out space and a cooling effect as well. So these generally cool the surface. That's what is expected. And the theory goes then that the corals or this marine organism that produce the DMS in the first place would be less stressed. So this theory is what's called the claw hypothesis. Stands for the authors of the hypothesis. Nothing special. Charlson, Lovelock, Andre, and Warren. So this hypothesis proposes a bioregulatory feedback. Okay. So if marine animals such as corals, or this proposed with respect to phytoplankton. If they're stressed, produce more DMS that interacts with the radiation and clouds and cool surface, so they become less stressed. So it's a negative feedback. Okay. Most literature thinks that this hypothesis does not exist, or this mechanism doesn't exist. Okay? There's been no good evidence suggesting that these creatures actually can do this, and most literature agrees with that. However, recently, a number of studies have suggested that coral reefs are an important source of DMS. Okay, so they're producing a significant amount of DMS. And a couple of other studies are thinking that corals are participating in this bioregulatory feedback. All of these studies are based on observations, okay? So the observations to basically correlations of like coral stress indices to aerosol, the aerosol optical depth, things like that. So they're not taking into account how complex this system is. What I've shown here. So this is a huge complex system, and especially between DMS and sulfuric acid and aerosol, there's huge non-linearities in those processes. And these observational studies cannot take into account these things. So what do we know so far? Observational studies suggest that coral reefs are an important source of DMS and maybe are important in the atmosphere. We know that the DMS climate system is very complex. We also know that no modelling study has been done to try and quantify this. And so no one has even tried to put coral reef DMS into a model, like a DMS climatology. It's unaccounted for in modelling, and no one specifically looked at this reef source. The other thing we know is that our coral reefs are dying. So this is what brings back to what Robin was saying before. One of the underlying aims of this thesis was to see if we lose our reefs, will there be an impact on the climate? Oh no. Okay. So apologies for this figure. It's just way too big and to display properly. What does this PhD achieve? Quantification of the importance of coral reef-derived DMS to atmospheric composition and meteorology across temporal and spatial scales using an atmospheric chemistry model. So that's my aim, or that's what I want to achieve, and I think I have achieved it, which is good. So the methods and tools that I've used, I have used a global climate chemistry model, and I've also used a regional weather chemistry model to answer that question of scale, so to look at the global scale right down to a local scale. I'm keeping Andrew's promise about some nice field campaign photos just a little bit. So we'll talk about that a little bit, but I won't actually go into too much. I'll also show you how I create a coral reef DMS source. Okay. So first of all, access. Access is the Australian Community Climate and System Simulator. So that's the climate part, coupled to the United Kingdom Chemistry and Aerosol model. So that's the chemistry part. Access is basically UM 8.4 for those who are interested, and it includes a sophisticated modal aerosol scheme called GLOMAP. So for those who like aerosols and detail, GLOMAP is GLOMAP is able to simulate all of these aerosol processes. Okay, and what I mentioned before about DMS eventually turning into sulfuric acid as a precursor gas is here. It's quite important, and then nucleating into the smallest size aerosol. So this is aerosol size on the bottom here. So GLOMAP is able to simulate all of these processes, which is quite important. Each simulation I did was long with a 1 year spin up that we chuck. It's quite coarse resolution, so I have monthly output with 125 degrees by 855 degrees and 85 vertical levels. It's constrained by sea surface temperatures, so they're fixed, not changing. And it's got prescribed emissions as well. Now, to do these experiments, I've had to do something a little tricky, not tricky really, but so I've one set of simulations, one pair of simulations that are nudged, okay, and nudged, when we're talking in modelling, means that we're constraining the meteorology, okay? We're not allowing the meteorology to feed back or to respond to what's happening in the model, okay? We're always bringing it to what happened in reality. And so what we call reality in this case is the reanalysis product. I've got one nudged simulation pair, all right? And then I've got some free running simulations. When we say free running, that means the meteorology is allowed to respond however it sees according to its physiodynamics. So because the meteorology is basically allowed to do what it thinks it should, it becomes very, very noisy. And so for that reason, I've done seven pairs of simulations with free running meteorology to try and reduce some of this noise or this sort of random model variability that we see when meteorology is allowed to respond. So we have an ensemble of 7 members with free and one pair nudged simulations, and you'll see why this becomes important later. Now, this has actually been a huge amount of work. I remember a little while ago, Alex Nels had said, "This is my PhD years took this one slide. This is basically it." So to do these simulations, basically took 298 days of computer time, and that's without interruption. You know, so there are a lot of interruptions in there. I screwed up a lot of things. So it's been a really long process. Yes, anyway, I'll leave that there. The other model that we've used is the Chem model. So this is a regional model, weather search and forecasting. It's an American model that's routinely used for forecasts and things like that. And it's to a chemistry scheme. And in this case, chemistry scheme is the CBMZ chemistry with a mosaic aerosol scheme. And I just want to point that if you remember in Access was a modal aerosol scheme, so that reflects what we see in observation. This scheme is what we call a bin scheme. So it represents aerosols bins. And one of the limitations of this model is that it can't represent the smallest sized aerosol that are quite important for the DMS system. It implicitly simulates them, but not explicitly. So this model ran it over October for 2016 to coincide field campaign we did. I've run it over 3 domains, which we see up in this figure here. Yeah. I'm mostly focused on, focused on the middle domain 2, which is at 9-kilometre resolution. Meteorology in WRF was also nudged, so not allowed to respond to the Bureau reanalysis product. And the chemistry restarted every 4 days from a chemical report model output. So to restarting the chemistry every 4 days is a similar thing to nudging, and making sure that the chemistry in the model doesn't go too far away from reality. Okay. So in WRF, I've just going to show you 4 simulations today. It's really only going to be 2 simulations. And they've had varying DMS fields, which I'll go into in a moment. WRF isn't anywhere near as intensive to run, so it only really took me about a year. But it's hugely data intensive. So one simulation is over about byte of data, so that can be difficult to manage. So, keeping my promise of some nice photos, we had the Reef to Forest field campaign, which involved the RV investigator, So the CSIRO National Facility ship with all sorts of science going on. We also had Airbox, which is coordinated by Robin, and it's a shipping container chock full of instruments that measure atmospheric chemistry, the mobile atmospheric chemistry lab. And you can see it was in the tropics, a very hard time with air conditioning. Yeah, it was just way too hot for it, really. So this field campaign, as I said, was September, October 16. Ships started in Brisbane and went around the reef up to Cairns and back down. And Airbox was situated downwind from the reef, because generally southeasterly at this time, in Mission Beach, right on the beach, which is pretty nice. So both of these campaigns aimed to observations that were relevant to the DMS cycle. That was their purpose. And these observations were used to evaluate WRF. Okay, so WRF, we needed to evaluate WRF to make sure that it could represent the DMS cycle that hadn't been in the literature too much. But I'm not going to talk to you about model evaluation today, sorry. And so ACS is also evaluated in terms of the meteorology, which I won't do either. And we also did sensitivity tests in both access and to look at how they responded to much bigger changes in DMS. It's kind of the test if you push something really hard, do one thing, and then you test again, and you just push it a little and see if it goes in the same direction. But I'm not going to go into those today, just in the interest of time. But you can ask me later. So, how do I actually put coral reef derived mass into a climate model? First of all, I figured out what action of every box in each model, so for access and then for 3 WRF domains as well, was covered by a coral reef. So you can see this sort of distribution here. So I then used this distribution to weight just a fixed amount of mass that we estimated come coral reefs, and I chose a quite high estimate of 50 moles, which doesn't really matter in this context at the moment. Just know there's a really high estimate of what coral reefs could produce, and basically times that by this fraction here, okay, to then figure out the contribution. So for WRF, this is what it ends up looking like for the 3 domains. So you can just see the coral reef DMS contribution here, but when you zoom in, you can start to see it much more clearly. So basically, for both models, the experiment is to compare a world with coral reefs to a world that doesn't have any, okay, and see what happens. So I'm going to start at the global scale now, and I'm going to work towards the local scale. All right? Hopefully everyone with me so far. So at the global scale, to represent what would happen if we lost coral reefs, I've shown all the plots as if coral reefs had died. Okay, so it might be a bit backwards to what you would think, but it's trying to represent mass extinction. We average everything over the entire globe to look at the global. Coral reefs contribute 1.7% of the DMS flux, or the contribution of sulfur to the global budget. So this is not very much. One of the sensitivity tests that we did earlier, we can do a rough calculation to figure out equates to about 0.01 degrees, which is very small and definitely not significant. So we can easily have our first conclusion here that coral reefs don't really matter to the average global climate. Okay, that's an easy one. But what about regionally? It's getting a little bit more complicated. So atmospheric DMS, and we've got just the absolute field here of the coral ensemble, remember, an average of seven simulations. Then we have the differences in the nudged sessions here, so ones where meteorology isn't allowed to respond, and the differences in the free simulations here, where meteorology is allowed to respond, and this is the average of the seven pairs, and where more than 5 of the 7 pairs agree on the change in sign, there's stippling, so those little black dots, okay, just as a sign of confidence, basically. So looking at the atmospheric DMS changes when we remove coral reef-derived DMS from the system, it looks pretty much exactly as you'd expect. You see changes where the coral reefs. Great. Same for sulfur dioxide. Basically, just seeing changes where there are coral reefs. Some little interesting things happening a little bit in the free simulation because of the meteorology, but we're not too worried about them at this stage. So that's all fairly straightforward. If we then start looking at the aerosol, so these are any particle greater than 3 nanometers, so very small particles, and including the big ones as well. What's interesting here, while the free and nudged simulations are still looking fairly similar, we can see that regions of only sort of small coral reefs, like in the Caribbean or Madagascar, are basically being washed out. So those reefs are too small to have any impact on the aerosol burden in these regions, and you see pretty much the same thing in the simulation. So we're not seeing much response in those ones. So for that reason, we're just zooming in on this area here, the Maritime Continent Australian region. And so far this all makes good sense. So like I was saying before, DMS can produce precursor gas, sulfuric acid, that nucleates into very small particles. So this is all starting to make sense. Thing is, and this is important for climate, is these very small particles don't interact with the atmosphere. Well, they're not as important for the atmosphere as big particles are. So big particles are the ones that are changing the radiation budget and interacting with clouds. The much smaller ones are able to do that, well, not well anyway. So even though we're in these sort of, I think when you average over the Maritime Continent Australia region, it's about a 5% change, and it is statistically significant as well. Even though we see that, it doesn't mean that that's going to have any effect on the climate. So now we look at some of the larger particles, and things are starting to get a little bit messier. So in the nudge simulations, you can see the signal washed out is getting quite weak. And in the free simulations, you can see that there's a lot of variability starting to happen. Okay, if we zoom in to just region of interest, and also I'm just going to talk about springtime now, because all of the other seasons had much with signals. There's a lot of signal variation from this point onwards. You can basically see the same thing. So there's the nudge simulations are fairly weak changes, and in the free, it's a little bit more enhanced, but there's quite a bit of noise. And that's something that we see throughout this, is that the simulations are tending to enhance these results, which is quite interesting, and might have interesting implications for the free running aerosol studies. If we then start looking at some of the climate stuff, so this is top of the atmosphere, outgoing radiation, if we pretend clouds don't exist. Okay, so we're removing clouds from the system at the moment, so we can just focus on how the aerosols interacting with the radiation budget. Okay, and you can see, if we just look at this, and if we go back in the free running simulation, ooh, wrong way. Oh no. Oh no. So that's the aerosol, and then we look at the radiation for the free running. We see that they, in sort of the Maritime Continent region, they line up, but we've got a lot of model agreed in over Australia, but we didn't actually see a huge change in aerosols over that region. So that makes us start to doubt these results a little bit. Regardless, we're going to push on to make sure we actually nail this and get to the bottom of things. So this is basically the amount of sunlight that's been reflected back out to space. So if you have reduced sunlight been reflected out to space, you'd expect to see more sunlight reaching the surface. Okay, oh, too impatient. That's exactly what we see in the nudge runs. Okay, where more sunlight reaching the surface. But in the free runs, something completely weird is going on. And when I first saw that, I was like, oh no, something's terrible. I've done something really stupid probably. But so if I just back, keep your eye on the front, you'd expect this to be red in the next slide. But it's also blue, which doesn't make much sense until you realize that water vapor actually absorbs shortwave radiation as well. Okay, so this is a zonal average of water vapor height, and the average across a latitude and just across that Australian maritime continent region. And what you can see is we've got increased water vapor right over this southern hemisphere tropical Australian region. Okay, so this increase in water vapor is absorbing all that extra short radiation that is in the system. It reduces the amount of sunlight reaching the surface. Yep. So the next question to ask is why are we seeing increased shortwave radiation? And my best answer at this stage is because the meteorology is allowed to freely run. So here are just a couple examples of things that we've looked at. Up the top we've got vertical velocity. Okay, so the coral field and the differences, and just show nudged runs here because, sorry, the free runs, because the nudge runs show any differences because they're not allowed to change. Okay, and we can see increased vertical motion over this Australian and sort of southern hemisphere tropic region, and that lines up quite nicely with where we're seeing increase in water vapor. What we also see down the bottom here, we've got meridional transport, so north-south wind, basically. And if we remember the Hadley goes up and down like this, so that's what we've got. We've got up top, we've got upwards motion and then downwards motion. We're seeing reduced transport south at the top and reduced transport north at the bottom. So we're seeing a weakening of this Hadley cell. Because the change in aerosol was so small and the change in radiation at the top of the atmosphere was also very small, with confidence can't say that these meteorological changes are happening because of these radiative effects. So we think it's more likely that it's just model noise, but it does highlight a few important things such as how complex this system could be and how important it is to make sure you really go through the whole system without just picking out your favourite parts. There was an interesting impact because of this changing meteorology, which is why we wanted to dig so deep into it in the first place. This rainfall, convective rainfall over the region for spring, and you can see that there's been it's about 11% increase in rainfall over Queensland for the region. And that when we first saw that, we were like, wow, that's huge. What's causing that? Because something we have to remember is the convective scheme in access and in WRF, when it's not at cloud rizzling levels, is the convective scheme doesn't know aerosols have changed. Okay, it can only respond to radiation, not the aerosol themselves. So this could have happened through radiation changes, but we don't have confidence that they were the actual cause results. So what do we know from this? Aerosol climate interaction is really complicated. We conclude that there's no significant direct aerosol effects that can be detected because of coral reefs. But it shows how important it is to consider this whole system, not to just take cursory glances at different parts. And it issues a warning to the oversimplification of aerosol climate interaction, and highlights that limitation of models and not having convective schemes coupled to aerosol. And if we just quick look at the indirect aerosol effects too, so this is the number of cloud droplets, okay? And they looked fairly similar to the CN, so the number of big size aerosol was. But if we look at large scale or low cloud fusion, so basically large scale processes, firstly we can see there's basically no large scale clouds or low fraction clouds occurring in this region at this time, which makes sense because we're looking at the tropics. And we can see absolutely no response. So this sort of again highlights that point that without the convective schemes being coupled to aerosols, it really limits aerosol studies in the tropic regions. But yeah, we're pretty sure there are no indirect aerosol effects from reefs here either. So moving further down the scale, we've seen that at the climate scale, so 10 year scales, there's no effect. But what about short term? What about day-to-day effects? Can we see any differences? So now we're looking at WRF, okay, and we're just going to focus on domain 2, so that the middle domain. Briefly mentioned before, domain 2 is at 9 kilometer resolution, so it's still parameterizing high cloud. It's still in a convective scheme. At domain 3, it was at cloud result scale, so we were hoping to get around that issue, but see, it hasn't made much difference anyway. This is atmospheric DMS, the coral run here, so we can see all the corals, and then the changes between two simulations, and remember these ones are another nudge as well. And we can see a difference in coral regions, and we can also see the influence of a sort of southeasterly flow propagating over the Queensland continent. But if we move along the system, so this is aerosol, sulfide aerosol mass, okay? We can see essentially change. The domain ranges haven't changed at all. And the other interesting thing we can see, which we think quite important for this region and probably a lot of other tropical regions, is these spots here. And these are all, can anyone guess? Coal power stations, yeah, which are basically populations and centres. Yeah, and there's a gas power station, I think it's this one up here, and a few other biomass burning hotspots. So what that picture tells us really is that anthropogenic or trivial sources, sulfide aerosol masses, are way more important to this type of aerosol than coral reefs. So that's an important finding. And the evaluation showed, I have shown it here, but even though we had predominant southeasterly flow for a part of time period, that southerly flow was still heavily influenced by terrestrial air masses. So the air had gone all the way around the continent and then just on a southeasterly back. So the terrestrial influence of the air mass in this region is really high, indicating that the small amount of aerosol that corals contribute is probably not going to be big enough. If we move through the system, we're basically the same thing. So these are the smaller size particles. Well, small as WRF can simulate them. Remembering WRF can only approximate some of these smaller ones. If we look at radiation balance, and there's absolutely no change in clear radiation. So just from changing aerosol. So that's a very clear conclusion that at the local scale, coral reefs play no no part in the atmospheric radiative valence here. And if we look at cloud droplet number, it's very noisy, but it's pretty much the same result. So I've just zoomed in on one grid box here to show you a little bit of the variability, because if I hadn't shown you the model evaluation, I think you would have been quite impressed. For some of these anyway. You can see, so the green one is the coral simulations, and the pink one is control. And again, you can see in atmospheric DMS, you can see changes, and you see big changes occur when there's high wind speeds, because the DMS flux depends on wind speed, with a few other things, but mostly wind speed. And then you're starting to see just no effect further down sort of the line of that system. So to summarize, global coral reefs don't have an impact on the energy. Regionally, there are small influence of very small sized aerosol, but these aren't able to influence the climate. If you move to larger aerosol sizes, there are insignificant small risks, and the corresponding changes in clear sky shortwave radiation are found to be unlikely to have an effect on regional climate. And no indirect aerosol effects were detected. And then locally, we find much the same thing. Okay, so if you do compare the access nudges to the wharf nudge one, they very broadly are saying the thing. So there are some model limitations in here, and that convective coupling to aerosol schemes is one of them. WRF explicitly simulating very small size aerosol is another, although we don't know exactly how that affected our results. I'm sure it has made an impact. But in conclusion, we can see that this is the first modelling study to quantify the influence of coral reef DMS, and that coral reefs play no role in regulating climate or weather. And we suggest that this is fairly solid evidence that no bioregulatory feedback could be possible, whether from coral or organisms or from phytoplankton, things like that. These results are in contrast with the literature on coral reef-derived DMS systems, but unlike those studies, we can account for the complexity of this system, which gives us this confidence. And in saying that, the findings of are agreeing with literature that focus on phytoplanktons, and that state that no bioregulatory feedback is possible. And that's it. Thank you.
So, questions for Sonya? Yes.
Can you use the microphone? This is going to be noisy.
Okay. Is it possible that the corals, it's like at the end of the chain? Other things have been on top of them, or in front of them, or them?
Do you mean that there are other things producing DMS that are more important? I don't quite understand the question, sorry.
Well, first thing is there any dimethyl sulfide produced you can measure?
Yes, and so the field
what's producing that?
Marine organisms.
So what your research is telling you is that the corals are largely indifferent to that?
No, so what the research is saying, so any algae or phytoplankton that you find anywhere in the ocean produces DMS, yep, as do coral. What we think is that reef contribution is important. So DMS produced by, DMS
okay,
on a climate scale is very important.
Yep.
So one of our sensitivity studies showed that all phytoplankton and everything died, for example. It result in a warming about 0.45 degrees. Okay, so they're really important for the big picture climate.
Yep.
But this small source just from corals and is negligible.
Other questions? Peter.
Yep. So the others get wrong. I think that the fact that there's a complexity here, which means that you've fully coupled system doesn't do it, and yet there's less literature that's saying it does. Was that kind of a relative study or a scale study or?
They've all been correlative studies, really. So they've done things like create a coral stress in the sea, and then correlate that with a lag to things like aerosol optical depth. Some of the studies tried to account for terrestrial air mass influencing the aerosol, but not as easily as what you can do in a model, I guess. And they've basically been a linear statistic for getting, well, not getting, but not capturing, especially at the sulfuric acid stage, that's so non-linear, where that condenses or forms. So,
as a matter of curiosity, get any of the same kinds of correlations that they've in the real world in your model?
I haven't been. I've tried a couple of times to kind of repeat what they did, but because I don't have an ocean, it makes it hard.
Yeah. Fair enough.
So, yeah.
Yep.
Thank you, Sonia. Nice talk. I think it's great that you highlight the complexity of the systems. So I think my question is on the complexity also on huge non-linearity between the aerosol and cloud interaction, and as you showed already at the end. Because in that region, particularly in the south of the Great Barrier Reef, is dominated by trade wind cumulus striking clouds to 40% of the time. I was just wondering, maybe it's not something that the cloud model can't resolve or simulate this cloud, but in your WRF model, in the most domain 3 kilo resolution, may struggle to produce those clouds with confidence. So the may contribute to the noisy result using, because you produce how to simulate the noise to begin with.
And that's
so
exactly
comparing
right.
noise to noise.
So we did do some evaluations of the cloud with access and in WRF. So WRF against the Himalaya satellite, and it did a pretty bad job of the clouds. Both in the cloud resolving and non-resolving scales. Yeah.
So what do you think will be way forward?
That's a really good question. I don't know. I mean, I think this study has been really nice in that we've had options from that field camp for the WRF stuff along the whole way along. So being able to bring stuff back to reality has been really nice. So I think for modelling studies, to make sure that they do have observations to ground them, observations that they're at least confident in anyway, that would be a good pathway forwards. In terms of cloud and aerosol modelling and model development, there's so much that I wouldn't know how to start it. Yeah.
All right. Thanks.
Thanks. You.
Yeah. Hi. Well done. That was awesome.
Thank you.
I was wondering, since you did sort of a regional study, do you think other coral reef regions could have different results, or you're pretty sure to be the same wherever the coral reef is?
Yeah, I expect so. So I picked this region partly because it's the biggest coral reef in the world, obviously, and because we had the field campaign. But as the access results showed, that maritime continent Australian region was really the only region where we saw a thing happening in the aerosol at the aerosol scale. So once got to aerosol, yes. So I think the other coral reefs just be too small. Yeah, that's what I think. Yeah.
Other questions? As if I have a quick one, which I should have. But just with Waterlink, can you remind me? Do the aerosols feed like change the water? Are they allowed to change the water vapor in either nudge or the free simulations?
Not in the nudge. I think water vapors. I mean, the nudging only nudges wind and temperature, but looking at the water vapor changes in the nudge runs, not much is going. I mean, aerosol can aerosol themselves interact with the water? I don't know that question answer. Water definitely would have an impact on the aerosol, but the growth, yeah. But yeah, how aerosol could impact water vapor, I don't know.
Mm-hmm. Well, thanks again, Sonya. That was a great talk.
Oh, almost forgot. Here are upcoming seminars. So 12th of February, there's a Masa Sugiyama, evaluating Japan's change and mitigation policy. And then if you want to look at the rest, you can go online and register along to the rest of our seminars, please. Thanks.
Questions?